Hello all, welcome to the seminar of subject probability theory and stochastic process. Today the topic is correlation. My name is Panindra. Coming into the topic. So in this seminar we can know how to understand the statistical relationship between signals, which is a very fundamental to signal processing. This presentation explores the core concepts, definitions, and applications of correlation and autocorrelation functions. So let us dive into the topic. The contents of this seminar are: we can see a brief introduction to the correlation and also the types of correlation, which are cross correlation and autocorrelation. We can see the definitions and mathematical formulation and also the applications of them, and a brief introduction to the power spectral density, which is in short form PSD, and its definition. Let us see one by one. Correlation tells us how two signals or variables are related to each other. It measures the degree of linear relationship between them. The correlation value indicates the statistical similarity or dependence between the two signals. We can see here, if both signals increase or decrease together, then the correlation is said to be positive. If one signal increases and the other signal decreases, the correlation is negative. When there is no linear dependency between these two signals, then the correlation is also close to the zero. So this representation helps us understand how two processes influence each other statistically. Let's see the types of the correlation, which one of them is cross correlation. Coming to introduction of the cross correlation. Cross correlation compares one signal with a time shifted version of the another signal. It tells us how similar two different signals are as one is shifted in time. This helps identify whether one signal is delayed or shifted version of the other. It is widely used in communication systems, radars, and signal matching. A peak in cross correlation, as we see here in the graph, indicates the time delay at which the signals are best aligned. So it measures the similarity between two signals. That is what cross correlation means. It shows how much one signal aligns with another at different time delays. Coming to the mathematical definition of cross correlation. Mathematically, for two signals x of t and y of t, the cross correlation is the expected value of the product of the two signals when one signal is shifted by a time lag of tau. The output is a function of tau, meaning that the correlation changes depending on how we shift one signal relative to the other. It gives us information about similarity and alignment at different delays. We can see here it is represented as Rx y of tau because we are taking for two different signals which are x of t and y of t. That's why we represent it as Rxy of tau is equal to expected value of x of t multiplied with y of shifted at tau. So function of time shift tau means the result is a function of time shift, which is tau, or we can call it a dummy variable or lag, providing information about how two signals align at different displacements. So we can represent its statistical similarity by using this mathematical expression. So coming to the autocorrelation, we will see applications later. Coming to the autocorrelation, it compares a signal with a time shifted version of itself. It measures how similar the signal is to its own past or future values by shifting. If the signal has two patterns or periodic components, autocorrelation will reveal them. When the lag tau is 0, the autocorrelation gives the average power of the signal. That's why we discuss power spectral density, which is related to the autocorrelation. So the only difference between autocorrelation and the cross correlation is autocorrelation compares with the other signal, while the cross correlation compares with the other signal, while the autocorrelation compares with the same signal or delayed version of the signal. It reveals predictability. It shows how much a signal at one point in time is predictable from its past values. That means past value or any future value, the shifted value. We can see the some autocorrelations of some signals with their delayed versions. Coming to the mathematical definition, a high autocorrelation at a particular tau means the signal strongly resembles itself at that time shift. This indicates the predictability or repetition. A rapidly decreasing autocorrelation suggests the signals quickly changes quickly and has a low memory. Autocorrelation is also used to detect the presence of the periodicity in signals such as speech signals and vibration signals. See here, the representation of mathematical representation of autocorrelation is or xx of tau is equal to expected value of x of t multiplied with x of shifted by tau. The only difference here is at the cross correlation we use our xy of tau, because at there we use two signals. Here we use only one signal which is shifted by tau and original one, so we are representing it as rxx of tau, which is autocorrelation. It measures the self similarity between them. It is also a signal power. As I told you, there is a relation between autocorrelation and power spectral density. Now let us see the applications of these two types of signal comparisons one by one. Cross correlation is used in time delay estimation, such as finding echoes or synchronizing signals. It helps detect known signals in noisy environments because similarity stands out even when noise is present there. It's used in image matching also. We can see here it is used in pattern matching. It is used in communication system where symbol timing recovery, carrier synchronization and channel estimations are there. It is used in system identification. Also it is used as feature extraction, used in speech processing and biomedical signals ECG and EEG to detect the repeating or correlation. The autocorrelation applications can be explained as follows. It is used to find the repeating patterns or cycles in signals. It's crucial in noise analysis because different noise steps have different autocorrelation shapes. It's heavily used in spectral analysis also. Here we can see the relation between the autocorrelation and power spectral density. Time series prediction. It is used in AR models forecasting, identifying how past values influence future values by the help of shifting. Feature extraction in speech recognition. This is similar with the cross correlation and system memory identification also. So let us see what the power spectral density means in brief way. The power spectral density describes how a signal's power is distributed over the different ranges of frequencies. For random signals, we cannot directly take a Fourier transform, so we use autocorrelation instead. By applying the Fourier transform to the autocorrelation of a wide sense stationary process, we obtain its ESD. This converts the signal's statistical behavior into a frequency domain representation. Wait, what is WSS wide sense stationary? That means when two signals are shifted, there is not any change. Stationary means they are stationary, no change is there. When the signal or a random variable is changed or shifted, there is no change in the behavior of that. That's why that is where wide sense stationary means. It can also be called as secondary stationary process also. So PhD represents how signal power is distributed. It reveals the signal characteristics, identifies the dominant frequencies, noise behavior, bandwidth, and power periodic components. It is widely used in communication systems, radar, audio processing, vibration analysis, and also biomedical signal analysis such as ECG and EEG. Let us see the definition or mathematical representation of the PhD. Here, the PSD shows the dominant frequencies, noise levels, and periodic components present in a signal. Engineers use PSD to analyze communication channels, as I told you. This is the mathematical representation. The PSD of a WSS random variable x of t is defined as Fourier transform of its autocorrelation Rx of tau. Rx of tau. Fourier transform of Rx of tau gives integral minus infinity to infinity Rx of tau into e power minus j omega tau d tau. We can also find the inverse Fourier transform, which is inverse relation between autocorrelation and PSD. Is we can find autocorrelation function from PSD using inverse Fourier transform. That means 1 by 2 pi integral minus infinity to infinity sxx of omega e power j omega tau d omega. Here sxx of omega is the power spectral density. This is represented in frequency domain. That's why we use omega. Thus, the power spectral density and the autocorrelation function are Fourier transform pair. This is our conclusion. The main we should understand that. Let us see the conclusion. Correlation provides the foundation for measuring similarity, dependency, and between signals. Cross correlation compares two different signals to find alignment, delay, and similarity. Autocorrelation compares a signal with itself, revealing periodicity, memory, and periodic predictability. Both functions help understand behavior of random processes. Power spectral density gives frequency domain view by transforming autocorrelation into a power versus frequency representation. Together, these concepts form essential tools in signal processing, communications, radar, biomedical systems, etc. This is what correlation, autocorrelation, and relation with power spectral density means. I hope you understand this. Thank you.